I want to take the time to work out one of the simple harmonic oscillator numerical problems. I've given you homeworks, so you should get to work on them and finish them before the solutions are posted, like I wrote last night. Too many of you are doing it after solutions are posted. That's not doing you any good. And then you guys send me an email, I'm doing badly, want to see you. Yes, you want to see me, I'll help you, but you have to help yourself. Do the bloody thing before the solution is posted, right? Otherwise, who are we kidding? So anyway, I'll work on that as far as one example problem goes. And then we have a lot of new stuff that we want to get to. But let me first do the thing that I wanted to do before I do the example problem. And this has to do with elasticity itself. Now this is a required topic because elasticity concerns something that is somewhat non-intuitive. At the basic level, elasticity has to do with elasticity of materials. Okay, so for example, when you go over a bridge, you will find a great many of the bridges are actually held by metal wires, and a great many metal wires are involved, and these metal wires tend to be quite thin relative to the size and the load that the bridge may be supporting. But these metal wires turn out to be obviously strong enough to get the job done and more. How do you know that? Well, you know that by analyzing the strength of the material. And this is where this business about elasticity comes in. And I just want to give you the basic physics of it. I'm not going to dwell on it. So it's a relatively simple topic, and essential idea is that, as I mentioned before, you have a spring, you have a mass, if you will, and we know that if I take this mass, let's say to this position, and let's say I stretch it by some length delta L, the spring constant here is small k, then it turns out by Hooke's law, the magnitude of this delta L will be proportional to the applied force. So this is the applied force, and how much it stretches is directly proportional to the applied force. Now suppose instead of having one spring, I actually have, maybe I'll put a bigger mass here, like a rod here, and I have two springs. And let us say, in this case, each of them have spring constant K, so they are equivalent springs, and I applied the very same force. So I applied the force here, and the force is F, and I applied the very same force. How much do you think that this system will elongate by compared to the previous one? The second one, half, because the force is the same. So therefore, one would naturally guess that if you have two springs, the stretch will be delta L over 2 per spring, and then two of them will add up to delta L. So you can think about delta L in this case as inversely proportional to the number of springs involved at a very simple level. So if you are thinking about an actual wire with a cross section, then that delta L would be inversely proportional to the cross section of the wire. If you have a thick wire and you pull it, that thick wire will have less of a stretch. If you have a thinner wire, that will have more of a stretch. So that's the idea. So if you have, for example, another thing is that if you have a wire that's twice as long in this case, so you have both of these springs tied end to end here, L and L, and you apply the same force, in this case it turns out that delta L will be actually proportional to L. So longer the wire, more the stretch. All of these are things that you can easily do in the laboratory, and you can make inferences based upon simple experiments and try to justify them intuitively. And that's typically how some of these things are set up. So if I now think in terms of wires, So I apply a force here, let's say the force is F, okay, and let's say this wire is elongated by some amount delta L here. And let's say cross-sectional area is A, then everything that I've written over there amounts to saying that delta L, first of all, is proportional to how long this is, right? Longer this is, more the stretch will be. That makes sense. So it's clearly proportional to L. Also, it will be, the stretch will be higher if the force is larger. So it is directly proportional to F, and it is inversely proportional to the cross-sectional area, because as we argued, if there are two springs, which is analogous to having a larger cross-sectional area, then the stretch will go down. So I would divide this by A being the cross-sectional area shown there. So very simply put, I can draw up an equation like this, a proportionality like this, using what we call joint proportionality, theorem of joint proportionality, in which delta L, we know separately is directly proportional to the force. We know delta L is inversely proportional to the cross-section, because the number of springs there ties with cross-section. And delta L is also directly proportional to how long the wire is. So if I combine them all, that's joint proportionality theorem. You can write this down. So in a nutshell then, I can think of it and write it like this, F over A. So I consider this side and say F over A is proportional to delta L over L. Proportional. The units are obviously not the same, because delta L is in meters, let's say. L is in meters. So this quantity doesn't really have a unit. This is force. You know the unit of force. Newton meter per kilogram meter per second square. And this is cross-sectional area, so that's meters squared. So this does have a unit. Force per unit area is something special. Do you know what it is? What is force per unit area? Pressure. Force per unit area is pressure. So this is really pressure. In materials, we don't call it pressure. We call it something most people suffer from, stress. But it's stress of materials, not my stress. And this is what we call strain. So you will find that in a great many discussions about various kinds of materials, if you want to look up the properties of steel or properties of aluminum, properties of platinum, properties of gold, properties of all these important metals that enter into our lives through the various devices and systems that we make, you'll find that even on Wikipedia, they'll tell you a great deal about their properties. And one of the important things that they'll tell you is the stress-strain curve. So typically the way it's done is strain is plotted along the x-axis. So this is your strain axis, and this is your stress axis, F over A. So this is stress-strain curve. So this is stress. And if there is no strain, you expect no stress if the system is okay. And as you increase stress, normally, as you increase strain, normally stress would go up, or vice versa. So it turns out that this only goes on up to a point. And beyond the point, the stress-strain linear, simple, nice law breaks down. So when we talk about elastic behavior or elastic properties of a system, this is the quote-unquote elastic behavior. So in elastic behavior, you should get a straight line like that with a finite slope if you're going to plot delta L over L along the x-axis, which is the strain along the x-axis, and the stress along the y-axis. Now, if you calculate the slope, one normally writes it as y, which is a special name. In this case, let me just make sure I'm writing it correctly. So I should be able to write then that F over A is equal to, so I'm converting the proportionality to an equality, Y times delta L over L. So this Y is called Young's modulus. And Young's modulus is specific to the material of interest. So for example, if you imagine a material like stainless steel, then it will have a certain value of Young's modulus. Correspondingly, if you take a material like nylon, which stretches more easily, it will have a very different value of Young's modulus. So I'll just show you very briefly. For example, if I take a wire, let's say I take a wire that's 1 meter long. So this is 1 meter long, and suppose my cross-sectional area, I'm not given the cross-sectional area, I'm just given the radius, and this is 0.5 centimeters. Then you can calculate the cross-sectional area, because that would be pi times r squared, r converted to meters, and that would come out to 8 times 10 to the minus 5 meters squared. So this is typically how these calculations go. And I'll give you a few of these problems, and you can work them out. And since the final exam is comprehensive, I'm required to ask you all these questions. Whether or not I think they are very important is not that big a deal. So now suppose I attach some mass over here, and say this mass I've attached is a large mass, say it's 500 kilogram. So just to give you a sense of things, this is a 1 meter long wire. 1 meter is about 3 feet. It's about 3 feet long wire, and 500 kilogram is a fairly large mass, right? So that's about 5,000 newtons. So therefore, if the mass is 500 kilogram, I can estimate that the downward force involved is of the order of 5,000 newtons. And it turns out then that if I write down my equation, my stress strain equation, I should be able to write the stretch that I want to find out, how much stretch it goes through delta L, as F over A times L over Y. So this is something I am directly inferring from here. So delta L is F over A and L over Y. That's what I've written. So if you insert the numbers, then you have this quantity. So this is 1 meter. It's F over A. F is 5,000. 5 times 10 to the 3. This is 8 times 10 to the minus 5. So obviously it's going to be a large number. So this piece here comes out to 6.3 times 10 to the 7 in the right units. I'm not going to write down the units right now. It's not critically important that we do that. The main point that I want to show you is that, so Y therefore plays a very important role, right? So if Y is very low, or if Y is very high, that controls how much delta L would be. And typically, for example, for steel, let's say, you can look it up. For steel, the Y value is approximately 2 times 10 to the 11. So that actually translates to a delta L, which is 3 times 10 to the minus 4 meters, or 0.3 millimeter. So as you can see, for a stainless steel wire, if you're putting in a 500 kilogram mass, which is obviously a very heavy mass, I wouldn't want to lug a 500 kilogram mass. The actual stretch this wire would suffer in terms of elongation is 0.3 millimeters. So that's very tiny. Correspondingly, if I took a nylon wire, for a nylon wire, it turns out that Y nylon is roughly 1 upon 55 of Y steel. So this was my Y steel here. So if I make it a nylon wire, obviously the elongation would be much larger, and then for nylon, my delta L would come out to 17 millimeter or 1.7 centimeter. So in a nylon wire, you'll be able to see the stretch with your eyes, whereas 0.3 millimeter is something that actually we cannot typically see with our naked eyes. So that, and we know that from intuition that nylon does stretch very nicely. So for example, in the Golden Gate Bridge, which is hung by all kinds of cables, this is exactly what's going on, and the thickness of the cable therefore is very important. In fact, the cables actually in Golden Gate are pretty thick, if you have noticed. Yes.
Does everything have
Everything that can be stretched or squeezed must have a describable Young's modulus. So in effect, every material has the Young's modulus. But the thing that I didn't tell you, that I want to tell you now, is that this only works up to a point. Okay? So if you now stretch it, if the strain increases beyond a point, then it turns out that this linear relationship actually falls apart, and this behavior, let me use another colored chalk. This behavior becomes something like that. It completely breaks down. So your elastic material has now become liquid-like. This would be behavior if it were a liquid roughly. And this regime, believe it or not, has a name. It's called the plastic regime. It has nothing to do with what we think of as plastics made out of polymers, but elastic and plastic have specific use in materials. Now what happens actually is when you get onto this plastic regime, the material has gotten strained so much that it's typically its cross-section is compromised, and it begins to stretch unevenly. So it begins to develop this kind of neck regions, and then it becomes prone to fracturing. Okay? So material fracture that happens is a real thing. So for example, before you board an airplane, the airplanes are inspected. So airplanes are inspected in a variety of ways, and how airplanes are inspected is an evolving technology. One way to inspect if there is a problem with the structure of the airplane is by sending ultrasonic waves, so very high frequency sound waves. And it turns out that if there are cracks, those high frequency sound waves are absorbed by the cracks, and from that you are able to infer that there is a problem with the material. Typically what happens is repeated use, which airplanes typically have a life of the order of 40 to 50 years before they're retired. So it's a long life. Ships also have very long lives, and they actually go through material fatigue, and that's a real effect. So in fact, if you look at the history of aircraft disasters, you will find that we have learned a great deal over time in understanding material degradation because of repeated use. So everything will suffer degradation, and sooner or later something will break, and that's something that actually is a real effect. So I will, as far as this particular topic goes, I'm not going to go further other than give you a few problems, because the level of understanding that is warranted in 101 is fairly rudimentary. But it is important to understand that large strains can actually cause a system to transition from elastic range to plastic range, and then it becomes prone to fractures. And of course, you can always calculate the amount of stretch and so on and so forth, and how much is okay and how much is not okay. All right? Any questions? Okay. Let me work out a simple problem using for simple harmonic motion, just to give you a taste of how to do these problems, because I assigned them So essentially, suppose you have a spring, just the way I drew it Tuesday, and the spring oscillates between two endpoints, P and Q, and this is the center, so I stretch it and let it go. Typically, that's how this would work. And suppose I give you some numbers. The spring constant K is 450 newtons per meter. It's a typical number. Spring constants can be quite large. The mass, so this effectively represents the mass of the spring, and this mass is half a kilogram, so 0.500 kilogram. And let us say the amplitude, which would be this amount or that amount. There's the maximum distance traveled to the right or to the left. So let me call it amplitude A. So A is, let's say, 0.040 meters. So at this point, when you do a problem like this, you immediately know that Hooke's law should work. So the force would be that way if displacement is to the right. So that will be minus K times x. And since force by Newton's second law can be represented as mass times acceleration, it's minus kx. So therefore, you arrive at the equation of motion, which is acceleration is minus k over m times x. And last time we wrote this is minus omega square x, where omega square is defined as k over m square, k over m, sorry. And omega is defined, therefore, as square root of k over m. That's the angular frequency. So this stuff should come out of your brain spontaneously the moment you see a spring. Now that you know all of this very well, the other thing that you should spontaneously make sure comes out of your brain is that the total energy is 1/2 Ka squared, because that would be the energy at point P or at point Q, right? Because that's when you suffer the maximum stretch. And at maximum stretch, we know that all the energy should be potential energy. And likewise, I should also be able to write this is at P and Q. I should also be able to write energy at point O. At point O, under the conditions of releasing at P, let's say, all the energy would be kinetic. So it's 1/2 m v max square. So I can calculate the maximum velocity that the system will have, which would be smack in the middle. And at any arbitrary point, it would be 1/2 mv squared plus 1/2 kx squared. So with the problem I have set up here, if I have to calculate the maximum speed, let's say maximum speed, somebody says maximum speed is going to be in the center if I release it at one end, right? Because once I release it, it starts to speed up and then slow down as it starts to squeeze the spring. So max speed would be from, if I equate this piece here to that piece there, so this would be 1/2 m v max squared is 1/2 k a squared. So therefore Vmax is equal to, I cancel the halves, so this will be k over m square root times a. And of course a can be plus or minus, Vmax can also be plus or minus because it can be going leftward at O or rightward at O. So both are possible. So at this point, if I put in the numbers, I have a value for A, which is 0.040. I know K and I know M. If I plug in the numbers, then what I get is a velocity of 1.20 meters per second. So this is a typical, very straightforward problem. This is the kind of problem I assigned for one or two of the homeworks. So suppose I also ask you, what's the speed at a specific point? Let's say what is the speed at x equal to minus 0.015 meter at this position. Clearly, 0.015 meter is much less than amplitude, which is 0.040 meter. So this is somewhere between P and Q. And the easiest way to do that is actually by relating k squared or Vmax squared to this, because this is for any point. And so I should be able to write, let's say, half k squared is equal to half mv squared plus half kx squared, which means that I should be able to write v as plus minus k over m square root a squared minus x squared. And since x squared is given, I can calculate the v, and if you put in the numbers and do the calculation, this comes out to plus or minus 1.11 meter per second. Observe that I have both plus or minus, because at any point, depending upon where in the course of its motion this oscillator is, it could be moving to the right or left, right? So therefore, that plus minus that I put in is the real plus minus, and it captures something that is going on, and it is not for any other reason. Similarly, you can calculate, for example, the maximum acceleration. That's, of course, very easy to do. You can look at maximum acceleration coming at maximum stretch. So when this is going to be a, you can calculate maximum acceleration. So all of these things can be computed. And that's fairly typical of the easier problems. What is not shown here is actually using the oscillatory motion, which is the cosine function. That's a little bit more involved typically. I've given you, I think, 1 or 2 homework problems on that. I want you to go over them. I can't show them in class because they take a little bit of time. The other topic I want to mention here, but I'm not going to get into the detail of it, has to do with resonance. Resonance is a very real effect, and a lot of bad things can happen because of resonance, and a lot of great things happen because of resonance. So what is resonance? Resonance is that, suppose you have this oscillator going back and forth, and you have set a spring constant k and a mass m. So the omega, right? Omega, as we discussed there, is square root of k over m. Omega is square root of k over m. So if you know k and if you know m, the spring constant and the mass involved, you can compute what the angular frequency is. And angular frequency omega is related to the frequency f, right? 2 pi over omega. T is 2 pi over omega, so f is 1 over t. So these are things that you should be comfortable with. Frequency f is 1 over the period t, and this is 2 pi over omega. So these are basic relationships we know. So at any rate, once I know k and n, I know omega, which means I know the frequency, or whatever. So now suppose I put in an external driver that pumps in energy into this oscillator in such a way that the oscillator gets a kick at the exact same frequency as its natural frequency omega. So, in other words, is going through this oscillation at, with angular frequency omega, and I now add an additional driver which would enhance this oscillation at omega. It turns out that this phenomenon, when you have these two frequencies, the frequency of the additional driver and the natural frequency, which came from square root of k over m, match up, the system hits resonance. And when system hits resonance, then two things can happen. If it's uncontrolled resonance, the system can actually break down. And almost all physics textbooks have a picture of one of the bridges in Washington State that collapsed because of resonance effects. The resonance came from wind. So the natural frequency of the whole structure was such that, of course, it had many frequencies, not one, but it had a sensitive frequency at a very low frequency range. And it turned out that they didn't know, this was 1930s or 40s, I don't remember, 30s I think, that the wind speed in that channel across which the bridge was built, I think this was near Seattle, had a frequency, so the wind would gust at a frequency that was very close to the bridge frequency. And it turned out that the entire bridge collapsed. And of course people died. There are pictures of cars falling off and so on. So, and this is nothing new. Similar incidents have happened in many places. So resonance effects can be quite damaging. You can have vibrations become unpredictably large if you hit a resonance. So when you design a structure, one thing you don't want to do is you want to make sure, is not make sure, about resonance. Any building, for example, a building like this, if it's vibrated at its natural frequency, whatever its natural frequency may be, will have a propensity to basically collapse. Okay, so this is a real effect. The other thing that's important about resonance that I want you to know, and it's not really important whether I write down any mathematics out of it, the take-home message is that we use resonance for various kinds of signal transmission, including, for example, in our regular cell phones and in the cars we drive and everything. We actually use resonance to use frequencies effectively for communication, for signal transmission, and for all kinds of technological purposes. So resonance, therefore, is a very important effect. The reason why I'm reluctant to do resonance in a more structured way is because it's mathematically not super simple. So I'll be giving you formulas that you may not necessarily get much of a chance to poke and understand from. But the main thing is that you know that the string equation is ma equals minus kx. That's something that we have talked about. But think about, to bring in resonance, you are now adding in some kind of other frequency, driving frequency, which is like this, let's say, where this omega is square root of k over m. So when you actually add this driving frequency, then the system can exhibit all kinds of interesting dynamics. Typically, this thing is done in a variety of ways, but the long and short of it is that the amplitude of the oscillations can actually go crazy. And the way it works is that the amplitude of the oscillation under driving, f0 is this f0, can go like omega 0 square minus omega square, where I would call this omega, well, I can call this omega in general, and I can call omega 0 as k over m square root. If I give you a resonance problem, I'll give you some formulas so you don't get stuck in them. So this is not something that I necessarily want you to memorize or anything. But you can see here what happens. This is the driving frequency omega, and this is the frequency of the oscillator, which is omega 0 square root of k over m. And this part I can't show you how the amplitude, so x of t, if you recall my discussion from Tuesday, is x of t is cosine of omega t plus phi. That's how we wrote it. And this a is same as that a, which is the amplitude of the oscillation. And what I'm trying to show to you, what I'm trying to argue here is that if you could solve this problem, which you obviously can't because it's not trivial to go from here to here, but if you could go from here to here, what you will see is that the expression for this amplitude turns out to be like this. What does it mean? It means that the moment this omega, this driving frequency hits omega 0, which is the natural frequency, this a will become what? A will become f0 over m divided by 0 almost. So that amplitude will have uncontrolled increase, and as a result of that, the system can become unstable. So this is basically the slightly more technical version of what I told you orally. All right. Any questions on this? Yeah. Phi was a phase. Remember at the end of the discussion on Tuesday, when I wrote down expressions for the oscillator's displacement, x of t, velocity v of t, acceleration a of t. Initially we wrote it as a cosine omega t, then we had some sine omega t, then we had another cosine omega t, we had omega squared and all those. If you look at the formulas, they should be there. But then I said that I don't have to start my oscillator at point P, which is what I did when I started the discussions Tuesday and today, right? In principle, I can start it anywhere. I can start it here, 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 here. So the solution should be valid no matter where I start. And to ensure that my solution is good wherever I start, that phase factor is added, because it allows you to go to the right point when you start your initial oscillation.
So,
it's a phase.
So it's a phase, so as pi, or do you?
No, right now it doesn't have any pi in it, but it's a phase, and it would be written in radians, right? So omega t, normally you would write omega. 2 pi plays a very important role, because 2 pi means one complete travel around a circle, or equivalently one complete period. So therefore, the phase comes from there. Nearly all books have some level of discussion as to why this omega and 2 pi they come up, and why we use radians. I did not get into that discussion. I have done it in some of my lectures, and I have also not done it in some of my lectures, and I find that it is rather difficult for the students to actually understand it, even if I try my best to explain it. But the most important message is, when you have a complete oscillation, that oscillation gives me what a period t is. So this oscillation of an oscillator along a line is equivalent to a round trip of a mass around a circle. They are mathematically equivalent. And there are various ways of showing that, and in fact your book actually has a discussion on that if you look at it in chapter 16. So that's where the 2 pi and the radian business connection comes from. But just read it up if you are not sure, ask me a question and I'll be happy to take you into it. All right. So one of the things that I want to discuss now is about sound waves. So sound waves and waves in general actually constitute one whole chapter. I tend not to spend too much time on waves, because there is a very, very important and difficult chapter coming up, which is on fluids, which is what is the next elephant in the room. So, and typically students have a certain level of challenges to go through in working fluid problems. So I like to get to that. So the amount of material I'll cover on sound will be rather limited, but so it will be first of all mostly concepts and then some small scale calculations. So we'll talk about waves in general, and we'll also talk about sound, which is one particular manifestation of waves, right? So think about something like a spring holding on a mass like this. And let's say I attach a string to this mass and then attach this string to a wall on the other side. Okay? So let's say I do that. So this is a simple experiment that we are trying to do. And now suppose I pull this down like that, just like I did it for that spring, and I let it go. So obviously what will happen is this is going to oscillate back and forth, right? Instead of oscillating this way like a pendulum, it's now going to oscillate like that. So it's a vertical vibration that I have initiated. If I do that, then what will happen is that the string that is attached actually will end up with some kind of waves going through it. And because the string is attached to the other end, you can't have any vibration where the string ties to the wall. So at this point you can't have vibration. Here the string is tied to this mass, so whatever this mass does, the string will do. But at the end of the day, what will happen is that you'll have some kind of a pattern set up. The vibration of this mass is in this direction, but the vibration that is going down the string will actually proceed in the other direction towards the wall. The point being that the vibration direction is perpendicular to the direction of sound propagation. So in this case, sound propagation would be rightward, vibration direction would be vertical, and that's an example of a transverse wave. Transverse coming from the vibration direction and the propagation of the wave direction to be perpendicular to each other. This is a rather boring example of transverse vibration. A more interesting example of transverse vibration, which we won't be doing in 101, is electromagnetic radiation, which you study later. So that's basically like light. That's radiation, which is not quite light, that's coming out of wherever my phone is. So it will have obviously ways of transmitting and emitting electromagnetic radiation at very high frequencies. So all of these things are actually going on from this. And electromagnetic vibrations actually have the electric and magnetic field vibrating like that and propagating. The propagation direction is forward. So that's an example of a transverse vibration. There are various other transverse vibrations that are for mechanical waves, like what I showed you, as opposed to electromagnetic waves. But electromagnetic waves are the most important example. Electromagnetic light, X-rays, gamma rays, whatever it is, all of those come from are at the electromagnetic end of the spectrum, and they have transverse vibration. However, what I want to talk about a little bit more now would be the longitudinal vibration. And longitudinal vibration is actually incredibly important for us. In fact, we wouldn't even survive without any of this, because if here I am talking to you, and here you guys are sitting in the class, whatever it is, what really is happening is that every time I open my mouth, I'm actually sending in some kind of a sound energy from my mouth into your entire body, okay? And it turns out that your ears are the ones that pick up most of this energy. But even if your ears were completely missing, I hope that doesn't happen, but if your ears were completely missing, you will still actually have, you'll still be able to perceive sound at some level, because our entire body can actually sense some amount of sound, believe it or not. Our hands can, our head can, and so on. But ears, of course, are the really special devices we have that allows us to hear. So what really happens? Well, every time I open my mouth, what happens is that I'm sending in some energy, and this energy manifests itself by creating these compression pulses that travel through the sound. Okay? So these compression pulses are so every time I say something, the air near my mouth gets compressed when I say something, and it is this compression pulse that hits your eardrums, tympanic membrane, or whatever that is, along with the rest of your body, and that's what you hear. And the hearing actually, just for the sake of this particular statement that I'm going to make is not important for 101, but the hearing actually occurs in the brain and not really here. So at any rate, this particular example, as you can see, is that of what is called a longitudinal wave, because the propagation direction of sound is this. And if you look at the air molecules, the vibration direction of air molecules are also in the same direction as propagation. So that's why it's longitudinal. So there are plenty of examples of longitudinal waves that we also deal with, including, of course, sound waves. So if you are, for example, I don't know if you've ever tried to talk in an environment where there is nitrogen or helium. If you have, you know that you sound funny. And you sound funny because you sound like a chipmunk. Your frequency goes high, And the reason why your frequency goes high is because the density is lower. So in other words, the density of air, the temperature of air, all of these play a role in controlling the sound that we put out and the sound that you hear. So our hearing can actually pick up many of these things. So much for the easier part of the discussion. Let me now get into the more technical part of the discussion. So let me now go back in the technical part of the discussion by considering relatively simple vibrations of strings, which is the transverse vibration problem that I laid out in the very beginning, between two fixed end volts. So if I have a string here, and let's say I plug the string and let it go, depending upon how I pluck it, one of the possibilities is that it can vibrate like this. So it goes like that, and then the other side, when it comes down, can go like this. We have all seen such kind of vibrations of strings. In fact, a musical instrument, if you're playing a guitar, for example, you can arrange to have vibrations like that. So in this case, let's say L is the length of the string, and if it's going to be part of a wave, then we know very well that the wave would go like this. So that would be my wavelength lambda, and here clearly L would be equal to lambda over 2. So drawing up this relationship is actually rather important. L is equal to lambda over 2. These 2 points where the vibration is 0 are called nodes. That's a node and that's a node. And this point where the vibration is maximum is called an anti-node. Okay? So you can have a vibration like this. Alternately, you can also have a vibration like this. And as you can see here, L would be equal to lambda. Okay, L would be equal to lambda. I can also arrange to have vibrations that are more intricate. For example, I can arrange to have vibrations with and you can see there is a lambda and a lambda over 2. So L here is 3 over 2 lambda. And I can go to L equal to, 2 lambda and so on and so forth. So first thing that I want you to do is therefore understand the connection between L and lambda. And then the fact is that we know that the velocity of the wave should be distance over time. And the easiest way to think about the velocity of the traveling wave pulse here would be the wavelength travel, which would be lambda, and the wavelength is travel in period t. Right? By definition, a wave travels an entire wavelength in period t. That's a full cycle. If you look at your notes, so in other words, this is the entire wavelength, this is your lambda, and the amount of time taken for the wave to go through the entire thing would be the period t. And therefore this should be lambda times the frequency, and therefore frequency can be thought of as v over lambda. That's a very important relationship because frequency is v over lambda, and I know the relationship between lambda and L, I can compute the frequencies. In other words, let's say in this case, the frequency would be f equal to v over 2L, because lambda over 2 is L, so this is v over 2L. In this case, the frequency would be v over L. In this case, the frequency would be V over lambda, so that will be 2/3 L. And so on. So for closed ends, as you can see, you can easily compute the frequencies once you know the relationship between the length and lambda. And by drawing a picture, you get there. Drawing a picture, you get here. And you get here. And then by simply remembering the argument that the velocity of wave propagation v is lambda over t, t being the period, this being the wavelength, and 1 upon t is defined to be the frequency, which is something that you have done before, then v is equal to lambda f. So in other words, you can then calculate the frequency. So why am I doing this? The reason why I'm doing this is because I want you to show that the frequency is the lowest here. And among these three examples, the frequency would be the highest here. Because 2/3 L is less than L, right? And that is twice L and so on. So frequency therefore goes down as the wavelength goes up. Now in a musical instrument, what we do is we actually we actually set it up in such a way that we control this lambda and we control the L. And sometimes we even control the detail of the string involved. So it turns out that there is an interesting relationship between, let me just give it to you. This is not something I'm going to derive, but if you have, let's say, a metallic string, just think about this as having length L and a certain mass m, then one thinks about mu as a symbol for mass per unit length. So mass per unit length tells you, it will depend upon the material of the string, right? So if you have a copper string versus an aluminum string, which is lighter and so on, the mu will change. The other important thing here is there is a certain amount of tension associated with the string. All of you who have played a musical instrument know that the instruments have to be tuned, right? You typically would pay quite a bit of money to your piano tuner if you play the piano to come out and tune your instruments. What is the piano tuner doing? Well, the piano tuner is actually adjusting the tension in the string. And tension basically is adjusted by, if you have one fixed point, by making sure the other point is tight enough such that the string is properly stretched. So let's say this string has a tension T that has been set up. It turns out that the velocity of sound as it would propagate through this string has a beautiful relationship that you can justify simply from dimensional arguments, and it turns out to be square root of the tension T over mu. So if your tension is not right, then the speed of sound will be different, and if your speed of sound is different, then your frequency will come out different. So that's the reason why the pianos are routinely, tuned. The tensions are fixed up such that you have the right velocity and the right frequency entering the picture. So I've therefore given you two relationships. One relationship has to do with the velocity as a function of string tension and the material, and the other has to do with velocity written in terms of wavelength and frequency. So these two often come together in various calculations. So at any rate, I will do a few problems on this, maybe one or two problems on this. It will be certainly posted. There is a great deal I can get into, but since time is limited, let me just point out one thing. Many of the instruments, musical instruments in particular, don't really have closed ends, especially wind instruments. String instruments like pianos and guitars and the various other string instruments typically have nothing but a dangling string, right? The strings are tied at both ends. So therefore you have the modes that could be described by the vibrations I have drawn there. But wind instruments, like clarinet for example, typically would have openings in them, otherwise you won't be able to hear a damn thing, right? So imagine for instance that if you have a wind instrument with one end open and one end closed, the simplest wave that you can have here, you can't have a vibration here because it's closed, so you can have maximum amplitude vibration around here, which peters out as you go to the other end. So if you look at this, since a wave is like this really gets you to that point, which means if this is L, this would be lambda over 4. So lambda therefore is going to be 4L, and since frequency is V over, and the frequency here actually would be V over 4L. So as you can see in clarinet, for that reason, you can hit very, very low frequencies because your control in the low frequency end goes up substantially because one end of it is open. So most of these musical instruments obviously are very complicated because you have holes in them, and by putting your finger in the hole, you close the tube, elongate it. By opening your finger, you break the length of the tube and shorten it, so you hit a higher frequency and so on. And even something as common as the piano has 288 strings in them. So the piano tuner earns his or her money pretty well. It's not easy to tighten those up. At any rate, I'm going to stop the discussion here as far as the sound goes. I mean, I can go on this problem because our very hearing is tied up with it. And as you age, your hearing goes down. Part of it is because your membranes becomes not as good, and the sound frequency it can handle goes down. So you guys can handle much higher sound frequencies than I can right now. Although my normal hearing, I guess, is perfectly fine. Anyway, all right, let's go to the quiz now.